So hi everyone, I'm Mahima. I'm a UX designer on Pair.
And I'm Yannick. I'm a software engineer on Pair. And can you hear me? No?
Can we try
All
again?
right, I'm going to try that again. I'm Yannick Asagwa. I'm a software engineer on Pair. Does that sound any better? Yep. Excellent.
Okay, perfect. So quick recap of what Pair is and what Pair does in terms of tools. We're a multidisciplinary group of researchers, scientists, designers, engineers, educators, and a whole bunch of really cool people. And our work begins with research, which leads to platforms and tools based on that research, which we then follow up with outreach and education. And our projects largely deal with model interpretability with methods such as TCAV and X-ray, and also the use of visualization for model understanding with projects such as Embedding Projector and the Graph Visualizer. We also use machine learning to solve larger challenges, such as visualizing algorithmic fairness, just on there, and trying to predict earthquake aftershocks. And the best part is that we release a lot of our projects in the open source world. And this means that our projects reach a lot of people. And so these are sort of, in broad terms, these are some of the audience groups that we frequently design for and create for. Researchers who are developing new models and investigating new methods, and also people in the industry who are building and applying models for production and delivering machine learning-powered experiences to consumers at large. And there's also this one group of learners, people who seek to learn about machine learning, coming from a variety of backgrounds, a variety of worlds, whether they're students or non-machine learning domain experts, and people who generally come to machine learning from a variety of angles with roots in their own domains. So this means that the tools that we create are essentially participatory tools. They have to be. And that means tools for all of these user groups, but also a variety of adjacent user groups, such as creative coders, people in the open source community who deal with accessibility demos and whatnot. And without further ado, Yannick is going to take the floor and talk about TensorFlow.js and tell us about how machine learning is introduced to a whole new class of users.
Thank you, Mahima. So, as Mahima said, one of the tools that we work on at Pair is TensorFlow.js, which is part of the larger TensorFlow ecosystem. And I'm going to try and explain what that is. And I'll start by trying to give a quick description of what the TensorFlow part is and what the .js part is and how they come together. So what is TensorFlow? It's Google's open source machine learning framework. And it was publicly released in 2015. And it's one of the most popular frameworks for building and deploying machine learning models. But what do I mean by the term framework? So we often think of the rise of machine learning as being driven by ever-increasing compute power and the availability of data. And while that's true, another important component is the software that allows us as humans to interact with these hardware and data. And that's where TensorFlow and other frameworks like it come in. These are building blocks that programmers use to create machine learning solutions. They're called frameworks because they bundle together lots of different useful components for doing ML, and because they provide a structured way of thinking about and expressing a machine learning solution. And the expressive power of these frameworks is really a large part of what enables people to be productive and to be creative when making machine learning solutions. So what we get to build out of matters. So for the .js part, so JavaScript is a programming language that's probably best described as the programming language of the web. And it's the most used programming language today, primarily because it's the main programming language available in browsers, of which most of you have one in your pocket, and almost all of you certainly have used one, at least maybe at home. So it runs on desktop and mobile browsers, and also on mobile devices natively. It also runs on servers through something called Node.js. And it also runs in desktop applications that are not a browser. And Magenta Studio is an example of that you saw earlier today. So that's running JavaScript, TensorFlow.js, not in a browser on the desktop. Despite its popularity today, though, it's had a rocky road. So especially in its earlier days, it was derided by many professional programmers as not a real language, leading to sort of questions like this on sort of popular programmer Q&A forums, or as a really bad language. So this is a Quora post with 81 answers telling you why it's a bad language, and maybe a few that say it's not, which leads to forum posts like this. Why do some of my coworkers argue that JavaScript isn't real programming? Or a post like this: how do I defend JavaScript when people call it not a real programming language? And this, if you read the message, it's a person who is becoming passionate about programming and JavaScript, and essentially being told that it's not a real thing that they're doing and that they're engaging with. So I think Douglas Crockford, it led him to a prominent JavaScript programmer, describes JavaScript as the most misunderstood programming language. And the assertion is in some of those statements is that if you are using JavaScript, you're not really doing programming, and you also can't be trusted to not harm the world of computing. So you really should stay away. And I bring this history up not to denigrate JavaScript. It's a language I really enjoy working with and I work with every day, but to draw some parallels to this theme of participation that's framing this symposium today. So JavaScript is a flexible language, and it's designed to be quite forgiving of errors. And this is really annoying to professional programmers, because that's like really hard to figure out what's going on. But this was intentional. It's in order to allow anyone, even amateurs, access to create things on the web. And this is sometimes to the chagrin and admittedly real inconvenience to those who may be already trained in how programming should be done. But I think it's one of its major strengths, and it's something that's allowed the web to be a wonderful, creative place of great things. And the web, the platform that birthed JavaScript, is fundamentally about participation. So it lowers the barrier to creating and sharing what you think is important, what you think is relevant. And that's the environment in which TensorFlow.js enters. So we believe with the right tools and scaffolding, even newcomers to the field can make interesting and relevant things, and given the chance, they can become the new professionals, or at least get to engage meaningfully in this technology and with these tools. So that brings us to TensorFlow.js, putting these two things together. So while TensorFlow is mainly used by the Python programming language, which is a language very popular in the data science and machine learning communities, TensorFlow.js brings these machine learning building blocks into web browsers and all the other places that JavaScript runs. And this allows the broader community of JavaScript developers to also participate in doing machine learning. And at this point, most developers are JavaScript developers, whether they like it or not. So some of its affordances include so things on the client side, easy setup. So if you're a developer in the room and you've ever had to set up a deep learning workstation and maybe had to install something called CUDA, it's much easier if you use JavaScript. To low latency real-time access to device sensors and to be able to make sort of interesting interactive applications. There's also a sort of privacy sensitive aspect, because you can bring the model to the device and not need to send the data off to a server, which can also lead to a lower deployment cost. So if you can't necessarily afford to run a server to do this machine learning inference, you have a new way to sort of distribute how these things get run. And on the server side, if you're already using Node.js, you get to use a single stack, which is always convenient. So there are three main ways to use it. You can run existing models, and we host some for you. Or you can convert them from Python models that you've trained, or you can even train them with AutoML nowadays. You can retrain existing models using a technique called transfer learning. And you can write models in JavaScript and train them from scratch. So let's look at those in a bit more detail. To make it easier for JavaScript developers to get started, most of whom do not have a background in machine learning, we provide some pre-trained models that can be used without needing to understand the low-level details of things like tensors. So running a trained model can be as easy as adding a couple of script tags to your web page and a few lines of code. So pictured here is a model we released called BodyPix that does person segmentation, sort of which parts of the body are which. And this is all running in real time, all in the user's browser locally, so nothing has to leave. Transfer learning is a technique that you can use to adapt existing models to new use cases. So pictured here is an example we have in our repo, where you can train a Pac-Man game to be controlled by your face, or really any other sort of object or thing that you have in front of the camera. And in this example, all the training happens all in the browser, right on the device. And finally, you can also author model code from scratch in JavaScript. So we're not going to go through this code here. This is not going to be a TensorFlow tutorial, but if you're curious, I can break that down for you later. But the point is, we do want to extend the expressive power of being able to create with code to this new developer community. We don't want to sort of limit them in that regard. Speaking of community, I'm going to highlight just 3 examples of things people have made with TensorFlow.js, one of which you just heard of, but I'm going to plug again. Teachable Machine. It's great. You're going to hear about it more during the breakout sessions. And it's a browser-based tool. Oh, the video's not playing. The browser-based tool to allow non-programmers to develop custom small machine learning models for their own use cases right in the browser. And it's a wonderful tool for prototyping and for exploring in a hands-on way some of what goes into making a machine learning model. So I hope you managed to get into that breakout session, or maybe you can check out a demo at the back. Another example I want to talk about is ML5. And this is a library, another programming library that's built on top of TensorFlow.js. And its tagline is friendly machine learning for the web. So it comes out of the Interactive Telecommunications program at NYU and aims to provide an easy on-ramp to machine learning programmers, to machine learning programming for artists, creative coders, and students who may not be on the traditional computer science path. And one thing I like about this project is that it's both able to explore creating sort of new APIs and approaches to make the programming aspect easier, but it's also able to allow critical exploration of machine learning from the perspective of artists. So helping to add that voice to this conversation around ML and giving them the tools to sort of use it hands-on. And the final example I'll talk about today is a research project out of the Mila group at Université de Montréal. And Chester, as it's called, predicts disease from chest x-rays. And it's delivered over the web. So the model is trained by scientists in a fairly traditional workflow, but it can now be distributed all over the world and used without uploading any data back to a central server. And this has benefits for privacy, but also allows a lower cost scaling model and ability to experiment without the need for a single provider to host or pay for the infrastructure or a research lab to sort of pay for that use case. And those are some of the kinds of things you can do with TensorFlow.js. So these are just a few examples. There's more available at this URL, some of the things you saw earlier today. So I've talked a bunch about model creation, but now I'm going to hand it back to Mahima, who will talk more about another area of Pear's work around tools to understand and evaluate machine learning models. Thank you. Here you go.
Thank you. Thank you, Yannick. Okay. Right, so I'm going to talk about the What If tool. A few of you would have seen some postcards behind there, and there are some stickers. And the What If tool was made by a bunch of us over here. James, raise your hand. He's right there, the builder, creator, supported by a lot of other people. Is Gabriel somewhere here? And a lot of UX research as well. But let's just get straight to it. So typically when we look at machine learning model performances, we look at a variety of very high-level global metrics like accuracy, precision, logarithmic loss, mean squared error, and so on. Now, these metrics are excellent at giving us a sense of how these models perform holistically. But they don't necessarily tell us much about how this performance changes when we move towards more human-centered models at granular levels, especially as we approach individual data points. And it's that sort of inquiry that we're interested in when we use human-centered machine learning models in projects and deployments. We're interested in questions that support a deeper understanding of these models, how they perform. And this also signifies a shift from testing with just global metrics to testing with simulations for groups and for individuals. And simulating different conditions is incredibly important because it helps us identify limitations in one way, giving us the opportunity to create more accurate and hopefully fairer models as well. But there are many ways in which that could go. It's hard to evaluate what sort of strategies might we use to improve our models. How can we compare multiple models? How do we compare multiple models, not just as they stand, but for groups and for individual data points? The kind of rigorous evaluations required are time-consuming, they're expensive, and honestly, they require a lot of laborious manual coding. The other thing is they also require a fair amount of imagination to actually explore this whole space of simulations. So we wondered, what would it be like to create a tool which would help people ask these kinds of what-if questions? So we started with a very simple test, editing something about a single data point and then checking if the model prediction changes. So over the course of 18 months, we worked with several teams, internal teams across Google, and realized very quickly that it wasn't just enough to edit a data point and re-infer model predictions. We needed a whole ecosystem of features to support this kind of inspection. We wanted to essentially build a tool which could debug a machine learning model or models individually, or one as a baseline, one as an experimental model, at different granularities, and also with minimal coding, which was a pretty high challenge. But we built the what-if tool, and this is an open source tool for probing machine learning models. It's got a graphic user interface, which helps you iteratively and intuitively stress test your models in simulated environments. So you're not really affecting the model. This is all post-training, but you're just stress testing the models. And we also take a black box approach. So we don't really care what the model architecture is, as long as it spews out some predictions on a given data set. We work with inputs and outputs just to understand where does the model stop performing, what are the big holes, the gaps that this model cannot perform in. And all of this happens in the browser, so we're not saving any data and we're not sending it anywhere. In this screen, what you see is the sort of default view that you land at when you arrive at the what-if tool. Over here, we use the power of Facets Dive. And we're looking at two models on the UCI census data set. One is a binary classifier, a linear classifier, and the other one is a deep neural network. And we're looking at scores. This is for model 1, and that is for model 2 up there. And you're looking also at an individual data point and the performance scores. So the what-if tool was designed to support a variety of workflows, but we specifically focused on the technical user. That's the data scientist, the machine learning researcher, the computer software engineer. And this is sort of what it looked like when we started out. And then when we started doing all these user studies, we realized it wasn't just enough to look at these technical roles. We had to look at the non-technical roles that they interact with, such as the PMs, the business stakeholders, the people who were making product decisions around these models, and just the larger stakeholder group. So while the original idea was to help machine learning researchers understand their models before shipping it, which the product did pretty well, we also expanded to make sure that it was more friendly towards the PMs and all the other stakeholders that they were interacting with. Another thing that happened, which we were pleasantly surprised by, was that we found that a lot of universities were using the what-if tool to teach core concepts in machine learning. And these were simple things like, what does it mean to train a model? How do you conduct a fairness analysis? Or how do you even look at, what does it mean to evaluate the performance of a model? And when we found that this was happening, we sort of flipped our strategy and introduced a lot more explanations, a lot more sort of robust documentation around various concepts in machine learning. We wanted the tool to be incredibly simple, and as the name suggests, quickly allow people to do what-if analyses just at the click of a button. At the simplest, you can edit a data point and run inference a second time and see how the model's prediction changes. This was a very simple feature. But then we did it in a more principled way, a more principled approach, which was partial dependence plots, in which case we're essentially, everything else being steady, we perturb one feature and check how the model behaves across all feasible values of that feature. For instance, here we see there's a little dip in the capital gain plot, and that's for the neural network. So our model has actually learned that as your capital gain increases, you're sort of less likely to earn more than 50,000. And then as your capital gain shoots up, you're probably going higher up. This was actually evidenced by the data that we saw later. The inverse of that was counterfactuals, described in Sarah Wachters' work, which uses a loan prediction model and asks what needs to be changed in a data point for someone to have actually gotten the loan. So there were two approaches to this. On one hand, it could have been an optimization problem where we tried to look for a hypothetical data point. But what we did was we implemented a slightly different strategy where we searched across a whole set of real examples to find the most similar example to an example of interest that was classified differently. And we also turned this into an entire visual tooling system with a single click, which highlights what some of the changes were, what the big differences were. It's a simple idea that we found internally at Google also supported a lot of powerful analysis. Another thing was we realized that our users were so diverse and they had so many different requirements. We needed to create a consistent mental model. So this is almost going back to what we heard earlier in the Magenta talk. But when we introduced this whole feature of comparing multiple models, we made sure that the visualizations that we picked could scale comfortably. And from UX studies, as we saw that models were diverse, data sets were diverse, each team had its own go-to visualization. So we also needed to support a whole lot of flexibility in visualizations. This was sort of the biggest lesson. So we started out as a TensorBoard application, and today we're in Jupyter, in Cloud AI, in Colab notebooks. But what we also did was we introduced various ways to specify not just custom models and custom data sets, but also distances, similarity metrics, and attribution methods such as TCAP or X-ray, or anything else that's relevant to your model and your data set. And this custom Python predict function can actually allow you to make remote calls to your server, and it also works with things like scikit-learn, PyTorch, and other custom libraries that you might be working with. So as I said, the What If tool not only allows you to look at individual data points and conduct analyses on those, but also on overall model performance. So you can actually slice and dice model performance on different subgroups of your data set. And you can play around with these different decision boundaries and these thresholds to see how your models perform as you change these. And then this was sort of one of the most exciting parts where we created an environment in which you could actually test different statistical definitions of fairness, asking questions like, what does it actually mean for this model to achieve something like demographic parity? And how does that look like for certain features that you're interested in? All of this is in a simulated environment within the workflow. So as I said, the What If tool is completely open source, and it's available on a variety of tools, platforms, and it's part of TensorBoard. It works with any Python accessible model. There's only one line of code that you need to begin with, and that's pip install witwidget. That's my shameless plug. And last but not least, this is the website. We have a bunch of demos that sort of will lead you into the entire space of what if analyses. And with that, these are our links, and we're happy to take any questions.